Okay, so here's a quick review of the rock cycle. We talked about this a little bit yesterday, but let's just review it one more time. So if we are looking here at a subduction zone, which that's what this is right here, when a continental plate subducts or takes over an oceanic plate. So this is a subduction zone. And when that oceanic plate gets subducted, we get towards the middle of the earth, and it's really, really hot, and we have a lot of pressure. And so all of that rock kind of gets mixed up and melted together. So that's where we have right here, we have melting, right? And then it starts moving up to the surface. And we have a homogeneous mix. Homo means the same. So all of this rock is like the same mixture. So you could break a piece off, and it's just going to be the same as the other piece that you broke it off of. So we're at the igneous rock stage, and then this magma breaks through the surface, forming all of these cool little volcanoes. And then when those cool, we have weathering. And so weathering occurs from wind, precipitation, people going hiking and chipping pieces of rock off because it's cool. So all of that, so the weathering of that rock, the igneous rock, goes down through the water cycle, right? Gets carried down by streams. And all those little sediments get deposited into the stream bed, which eventually deposit right here along the ocean. And when you have the compaction, okay, then you get sedimentary rock. It's not until that sedimentary rock gets subducted into this zone right here that it becomes metamorphic. Metamorphic means that it's had heat and pressure applied to it, so it has that cementation and compaction. And both sedimentary and metamorphic rock are heterogeneous mixtures, so they're different. So one piece of rock may not be the same as another piece of rock. Here's another look at just a really simplified version of the rock cycle. So no matter where you start, right, if you start here at igneous rock, through weathering and erosion, it will turn into sediments. And those sediments, through compaction and cementation, will go into the sedimentary rock. And with applied heat and pressure, it will go to metamorphic. And that metamorphic, after it's melted, will turn into magma. The magma will cool, turn into igneous rock, and it will continue. If you take that igneous rock and apply heat and pressure, right, it'll go back into the metamorphic. If it melts, it goes back into magma, and so on. We also did the crayon rock cycle, if you guys remember that. So when we had our whole crayon, right, each color was an igneous rock, right? So if I had a purple crayon, that was a heterogeneous mix. If I color with that entire crayon, what color is it going to be? Purple, right? It's not going to change halfway through the crayon. When we ground it up, that was us creating our sediments. And when we applied those sediments together, so we mixed a bunch of different colors together, we got that sedimentary rock. And then when we applied heat and pressure, right, we put the boiling water and we dipped the foil in the boiling water, we created metamorphic rock. So it was a harder material that was all mixed together, but it was the heterogeneous mixture. So if I color with one side, it might be purple. If I break it apart and color with a different side, it might be yellow. And then if we were super fancy, super cool, and we mixed it all together totally perfectly, it would turn back into igneous rock. Obviously, it's not going to be purple or yellow or blue. It's going to be an ugly brown color, but that's okay. It's all still the same. Now let's talk a little bit about seafloor spreading. The boundaries that we have, okay, we have the strike-slip boundary right here. That's when you have the strike-slip fault, where you're lined up with the transform boundary when you have lateral motion, so it moves from side to side, and the rock layers do line up. And then we have the divergent plate boundary, okay, and that creates a normal fault. So divergent means it's coming apart or pulling apart through tension. And then we have a convergent boundary, which creates reverse faults, and that's compression, or the pushing together part. So if we look at seafloor spreading, okay, we have the mid-ocean ridge right here, which is what we talked about, and this is a divergent plate boundary. So the plates are pulling apart, as you can see from these arrows. Okay, so that lithosphere, that top layer, our crust, is always in constant motion, and they're just little pieces that are kind of floating around on top of the asthenosphere. So from the mid-ocean ridge and our divergent plate boundary, okay, we end up moving that oceanic crust towards something else. So in this case, we're moving it to the continental crust. Oceanic is more dense. Okay, it's the shallower of the two, but it's more dense, right? It's really compact and really dense, so it's really heavy. So it's going to suck underneath or be subducted by that continental crust. So when that subduction zone happens, okay, that's a convergent boundary, or when the plates come together. When that happens, we end up getting subducted down here where we have a lot of heat and pressure, and that heat creates little volcanoes, right? So we end up breaking through weak spots right here and forming volcanoes. So when that magma busts through the surface and creates new land mass, right, we have more continental crust. Eventually what happens? Eventually, like we just talked about in the rock cycle, we have weathering that occurs. It gets, taken back to the oceanic crust and it's subducted again. So really, there's always land mass that's forming, but there's always land mass that's being recycled. So we're really not adding or subtracting anything. We're just changing its form. And then right here, we kind of talked about how the Hawaiian Islands are formed. So the Hawaiian Islands are floating over that hot spot. So that oceanic crust is floating over a hot spot. And so over years and years and years, that magma is breaking through the surface, creating new volcanoes. The farther away you are from that hot spot, the more weathering that has occurred, and so the smaller the islands. Okay, let's take a look at some important equations that you're going to need. So speed equals what? Speed equals distance over time. So anytime we have an equation, we could always put it in that triangle. So you draw your triangle, you divide it into 3 sections. Speed would go here, distance is on the top, so it's going to go here, and time is underneath it, so it's going to go here. Anything above something else is going to be divided, anything next to each other is going to be multiplied. So here's a multiplication, and here's the division piece. So if I have any 2 numbers, I can calculate the third number. So let's say I have the speed and the time, and I want to calculate distance. If I have a speed of 10 miles per hour, and I have a time of 2 hours, how far have I traveled? Well, my equation tells me that I'm going to multiply those together because speed and time are next to each other right here, right? So what's 10 miles per hour times 2 hours equals a total of 20 miles. Okay, density. Density equals, draw your heart and cut it in half, mass over volume. Same thing, put it in your triangle, density, mass, volume. So if I have mass and volume, I divide it, right, because one's on top of the other. If I have mass and density, I divide it because they're on top of each other. If I have density and volume, I would multiply them together. Mechanical advantage, same thing. Mechanical advantage equals the resistant force over effort force, or resistant arm over effort arm. Same thing, put it in the triangle. Mechanical advantage, resistant force, effort force. And remember, the resistant force is the load, or what you're trying to lift. Okay, the effort is how much effort you have to put into lifting that or moving that object. And the mechanical advantage is what that simple machine will give to you.